Good evening, everyone. So today I want to talk about artificial intelligence through a journey of three industries. I'll start with autonomous driving. I think it's the most exciting one and kind of the microcosm of all what you need to do in narrow AI. It has all the elements that you need to solve if you want to have a narrow AI. But I'll talk about other industries as well, three of them. I'll leave it as a surprise what are the other two. So, and I'll talk about what and not how. I'm not going to dive into how things are done, but which I think is less interesting. I'll talk about what are the things that can be done, okay, which I think is more interesting. So, kind of the topic is that if computers can perceive the world, through cameras, through microphones, so listen and see. If computers can perceive the world at high levels of performance, and can make decisions at high level of performance. Those are the two main areas of AI. Then how can that serve us today? Okay, so I'm talking about the current state of the art. I'm not talking about science fiction, what will happen in 10 years from now. I'm talking about today. What can we do with today's technology that is transformative? Not targeting ads when you are the internet, but something that is really transformative. And then, what would be the next, and I put in parentheses, near-term frontier. Again, not the science fiction, not 10 years from now, what will be 2-3 years from now? Well, what can we expect to happen, which is, again, transformative? So we will start with autonomous driving. So first, why autonomous driving is so relevant to the pursuit of artificial intelligence. First, we have perception. In order to drive a car autonomously, the car needs to see. So we need to understand the environment around the car at very, very great details. All road users, whether they are motorcyclists, bicyclists, cars, trucks, and so forth. The drivable path and all the semantic meaning around it. This is a road boundary, this is a road, this is a highway exit, traffic signs, traffic lights. Everything around the car. So this is perception. This is the part of the perception. Then there is action. Assume that we know what's around us. Now we need to make a decision. Right? It's kind of a multi-agent game. There are other agents on the road, and I need to change lane. If I need to change lane, then I'm affecting the motion of other users. In congested traffic, you change lane. Somebody needs to slow down in order for you to fill the gap. So you are creating a gap rather than detecting a gap. So we're talking about decision making in a complex environment. Why it is complex? Because people can die. If you make the wrong decision, you can kill someone. So we're talking about the highest level of decision making. And decision making is also one of the main pillars of AI. We normally see it when playing games, playing chess, playing Go. Those are decision makings. But it's very, very similar. Okay, so you have those two main pillars of AI. And what will be the promise? So first you can have an accident. I put in parentheses almost. You can never guarantee zero, but accident-free world. Because above 90% of accidents is human error, not mechanical error. We either have a lapse of judgment when we make actions, or we have a lapse of perception because we are focused on something else, texting or just dozing off or something like that. So we make a lot of errors. And there's more than 1 million fatalities a year. So this is a big thing. We're talking about data revolution powered by cars. So imagine that you have a camera in every car and the camera is intelligent. And let's just entertain the thought that the ability of the camera to perceive the world matches human perception. It's not true today, but let's entertain that thought. So now you have an intelligent agent seeing the environment, making notes, and sending those notes to the cloud. The road marking needs to be repainted. The traffic sign has been fallen that needs to be fixed. Somebody's being mugged. Call the police. There's a pothole. You need to call the city infrastructure to come and repair it, and so forth. So you can see how you can power smart cities if you have all those agents always observing the world and making notes. Okay, so this is a data revolution. We're talking about revolution transportation as a service, the Uber and the Lyft of the world today, the ride-hailing, ride-sharing, revolution of car ownership and utility. Cars are underutilized. Don't know if you know, but 96% of the time the car is in a parking lot. So we buy a car for such a huge cost, and only 4% of the time we make use of it. But if you have an autonomous car that can drive without anyone in the car, then the utility goes up considerably. I can take the car to work, send the car back home, take other household members to where they want to go. Car come back in the evening and takes me back home, or I can drive it or take me back home. In terms of Uber and Lyft, it is known that 80% of the cost per mile is the driver. Another 18% is additional cost. What is left is 2% as a profit, and then there is price wars between the operators, and nobody makes money. So, and we all know that, those companies are public today, Uber and Lyft, and they're very open about it, that they don't know how they're going to make a profit. But if now you remove the driver from the equation and replace it by CapEx, capital expenditure, then you have something that has a return on investment, and you can then reduce the cost per mile to levels that are rival with public transportation, because that public transportation is subsidized. So being able to compete with public transportation is something that is transformative. So that could change transportation in cities that, people will not need to own a car if they live in a city, because the cost would be lower than car ownership and lower than transportation. So I hope that I convince you that if we solve this problem, we're talking about something transformative. Saving lives, changing the way cities are designed, revolutionize transportation. Okay. So let's start, and now I want to focus about, what are the really big issues there. Okay. So first, I'm going to show you a clip on my way to work in Jerusalem. You're going to see how the Israeli driver drives, but the Israeli driver, I think it's a good sweet spot, because the driving in Israel is similar to the driving in Italy, in France. It is sufficiently assertive that if you drive here, you can drive almost everywhere in the world. Right? So it's a very good place to test things. Not India. So there are a few places that are more assertive and aggressive, India, Thailand, but most of the developed world, if you drive in Israel, you can drive there. Okay. On the other hand, if you drive in California, then you drive in California. There's nobody is going to drive like that anywhere in the world. All right? So now let's look at this clip. Let's say, one moment. Let's look at this clip. So you see this car is squeezing its way in. Now you're going to see the next car is not going to succeed. It's going to try to merge to the left, and then at some point we fast forward this clip, and this poor guy or woman, I don't know, will not be able. Okay, so when you're talking about decision making, this guy here will succeed, but is going to make a lot of effort. Again, we're fast forwarding. And so imagine long-term planning. This is really long-term. This is minutes, because we're fast forwarding the clip. Right? It's a struggle. So now imagine an autonomous car in such a situation, right? Because you have to be able to handle this. Why? Because you can say, okay, autonomous car could be very, very conservative, would drive slowly. That's it. It goes on and on. Okay. So you can say, okay, why drive like a human? Drive like a machine. Drive slowly. If I want to change lane, I'll wait for a gap. I'll change lane only when there is a gap. I don't interfere with anyone's motion. That's fine. But the problem is that you'll block traffic. You'll not be able to move. Now imagine you are a user, you're a customer, and you're ordering an Uber with a robo-taxi, right? You wouldn't hop on that vehicle if you know it's going to take 3 times as much to get to your destination, because this guy is driving like my grandmother, right? So in order to create a business, in order to create a service, it has to drive like a human. So what are really the key issues? One is perception. How do we? I'm not talking about human level performance. That's first of all ill-defined, and we're not there yet. I'm talking about human level accuracy, which is something that is measurable. So what do I mean by that? If we make a perceptual mistake that causes an accident, and what we are interested is fatalities. Right? Because imagine a machine killing a person is something that is very, very problematic. Right? So a perceptual mistake that causes a fatality, this should not exceed human probability of failure. Because otherwise, society will not accept a machine that can kill people at a higher probability than people killing people, right? Even killing people at the same probability of people killing people would not be acceptable. But lower than that, forget it, right? And I'll show you in a moment that this is a big issue. Right? Second is kind of trade-off between safety and usefulness. So if you are making an action that causes an accident, this is something that should never happen. Right? A lapse of judgment is not something that society can agree with machines. A machine should not have any lapse of judgment. So a machine should not make an accident that causes, should not make an action that causes an accident. How do you go and guarantee this? Because we're talking about a multi-agent environment. Right? Sometimes it's not my fault. So how do we go and guarantee anything about accidents? So let's first tackle the first issue, the perception. So when you look at the AI's pattern recognition of today, it's very, very impressive. I'm not going now to show you clips of machine perception. Believe me, it's very, very impressive. But, and it can handle, lots and lots of rich situations. Almost anything you can think of, we can do today with machine perception. But the challenge really is accuracy. So what do I mean by accuracy? So let's look at human statistics. When you're looking at the probability of a fatality per 1 hour of driving, the human statistics, it's 1 to a million. So you're driving your car, the probability that you'll be involved in a fatality in the next 1 hour is 1 to a million. That's human statistics, okay? So now let's assume that human get into accidents, sometimes because driving under influence, because of a dozing off, texting or whatever. Machines would not have this problem. So if we remove that, then it's safe to say it's 10 times better. So the probability of a fatality in 1 hour of driving would be 1 to 10 million. Okay? So it means that we need to reach a mean time between failure of the robotic agent of 10 to the power of 7 hours of driving, just to reach human probabilities. So, okay, is it difficult or not difficult? Well, we do have a bar, and that bar is driving assist. So for example, today, driving assist, almost new cars come in with a driving assist built in, and that driving assist can apply the brakes before an accident. It's called AEB, autonomous emergency braking. Now for the car industry, it's very important that the level of false positives would be asymptotically zero. They don't mind if there are misses, because the human is still in control. You are driving the car, it's just another set of eyes and brains that would take control if you are not taking control, because you are dozing off or something, right? But you are still in control. So if there is a miss of detection, of course, well, it has to be a small percentage of misdetection, but it's not that critical. But if there is a false detection, it's hugely critical. Imagine you are a driver driving leisurely. You didn't buy the system. It comes built in because they need the star ratings. You are not even aware that you have the system. All of a sudden, the car, without any reason whatsoever, it saw a shadow on the road and thinks it's a car, applies the brakes at 0.6 G. Right? You'll be scared. Right? And you go take the car and return it to the dealer. Right? So the probability of a false positive here has to be very, very low. So now the question is, since we are the major supplier of these systems, we know what are the statistics. What is the probability of a false positive in an AEB system? Now the AEB system has the latest machine perception you can think of. Deep networks, whatever buzzword that you have is there. Okay? So what is the probability? The probability is very, very impressive. It's 1 to tens of thousands of hours of driving. So it's in a lifetime of a car. So 10 to the power of 4. But we see here that we have 3 orders of magnitude difference. We need to reach 10 to the power of 7. Not only falses, but also misses. So we are not there. So the way to handle this is to create separate subsystems. To create a subsystem based only on cameras, being able to do an end-to-end autonomous drive only with machine perception of using cameras, and then create another subsystem with radars, lidars, and other sensors. And then it's kind of independent, you can never prove that it's really statistically independent, but it's kind of independent because these are different sensor modalities. And now the mean time between failure is a multiplication of the mean time between failures. So the 10 to the power of 7 becomes 10 to the power of 3.5, which is now a few thousands of hours. And this is something that is within the current state of the art. And remember, the first slide that I mentioned is I want to talk about the current state of the art. What can we do with the current state of the art? I'm not saying that in the future we'll not be able to reach 10 to the power of 7 with a single modality. I believe we can, but not today. So if we want today, then you need this mean time between failure. Okay, so now let's look at the other challenge, which is the decision making. Now the decision making challenge is really mind-boggling. And here there's no easy escape route, just like I did with the perception by having two separate subsystems. Now, why it's mind-boggling? Let's assume that we have the maneuver of changing lane. So there needs to be a gap between two vehicles for me to enter. So programming a robotic agent to find the gap is one thing. You found the gap, and then you plan a trajectory and plan the control in order to enter smoothly into the gap. So this is well defined and so forth. But we all know that humans create gaps. Human drivers create a gap because in congested traffic there's not going to be a gap. You have to create a gap. So now if you are creating a gap, you are raising the probability of an accident. Right? I'm causing the other driver to slow down. That other driver didn't slow down and hit me. What do we do now? Okay, this is a big issue. So I can say, okay, I'm not going to do that. I'm only going to detect gaps. But that will bring us to the position I said before, that these systems will not be useful. In order to become useful, you need to be able to create a gap. Okay, and this creates an issue of safety. Right? Now, humans balance between safety and usefulness. Because if we wanted safety to be absolute, then we would drive at 10 kilometers per hour also on the highway. Right? The slower you drive, the less probability of an accident. Now, humanity wants cars to create flow, right? So we want throughput. So we're balancing usefulness and safety. So we need to be able, machines to do the same and work with regulatory bodies to agree with us on a model how you balance safety and usefulness. So this is a catch-22. Agility raises the probability of an accident. Now, so let me show you how this is I'll show you a few clips. So what we're going to have here on the right-hand side, you're going to see the top view. So this is only cameras. You're going to see the top view. The blue car is the robotic agent. All those bounding boxes are other cars. You see here 3 front-facing cameras, front and 2 corners. So you'll get an idea of what's happening. And you see also the view from the driver looking outside. And you can see the driver is not going to hold the steering wheel, so that I'm not cheating you. Now, there are going to be color codes, those white rectangles. So when a white rectangle becomes red, the robotic car decided to give it way, let it pass. If it's green, the robotic driver decided to push its way, to take the right of way. Now, when it's green, the robotic agent tries to push its way, but it can make a decision that it will not succeed. So it will relent, and then it will turn from green to red, meaning we let it pass. So let's have a look at this. Right. Driver came out of the car, and now the robotic agent understood that there's a blockage that needs to change lane. Congested traffic, and you see it's pushing its way through, and that car on the left, which was green, had to slow down. So in order to push your way in congested traffic, you need to be agile. You cannot just find a gap. You need to create a gap. So this is how it looks from above. It's not the same scenario, a similar one. There is a blockage. This is the robotic car. You see the Mobileye logo on top of it, and congested traffic, and it will start pushing its way. And this is how it looks from the inside. Okay, that's now it's doing all, and you can see the red and the green. Right? Okay, so this congested traffic is a big challenge. Here, the last one in this section I'm going to show, we are going now to enter, this is more city driving. This is Shai Shalev Schwartz, also professor at our department. And now look at the number of cars there on the T-junction.
You said he was a professor?
He is. He's also the CTO of Mobileye. And now we're taking left in this, see how congested it is. So it's unprotected left turn, there's no traffic light. Okay. Okay, so these are the kinds of scenarios that you need to handle, and you can see how these kinds of maneuvers raises the issue. Okay, what do I do with accidents? What kind of guarantees I can give about accidents? Because when we are interfering with the motion of other road users. So I'll skip this one. So 2 years ago, we wrote a paper about this issue and made it public. So that's why we wrote the paper, in order to deal with regulatory bodies. Okay, and here it is important, because you need to now engage with regulators on this issue, because you don't want to wait for an accident to happen, go to a court with a jury, and then you never know what's going to be the end of it. And if you have a fleet of thousands of robotic vehicles, the chances of an accident, every day you'll be at court. So you need to start engaging with regulatory bodies, but you need to engage with the model. And the way we designed it is, we said that we can codify the human judgment of driving. Although it looks very, very complex, we reduced it to about five principles, and then showed empirically, through looking at databases of accidents, that this model is sound. It covers all the known accidents, that we're talking about millions of accidents that were covered. It allows to balance soundness and usefulness, and it has theoretical guarantees. So it means that it will satisfy the inductive principle. That means if you're making a decision and this decision is safe under this model, you know that there's not going to be a chain of events that will result into an accident later because of this particular action that you did. Now, what's the basic idea behind this? The basic idea is to, and this again, it's inspired from the way humans think. When I'm driving in the highway and there's another car on the next lane, I'm making an assumption that other guy is not going to spontaneously turn the steering wheel and hit me. Because if this is a possibility, then I shouldn't be near him. Then I can never drive in a highway. I can never drive in a congested highway. So we're making this assumption about what is reasonable to expect. And then under those assumptions, we take the worst case. What do we mean by worst case? Why, for example, we keep safe distance to the car in front of us? We keep safe distance to the car in front of us because we say that in the worst case, the car in front of us is going to apply the brakes unpredictably. Now, what are the assumptions we're making? We're making assumptions about what is the braking force. Is it going to be unlimited braking force, 10G braking force? Then I need to keep a very, very large distance. I said, okay, 1G braking force is a reasonable assumption. Of course, we're not making those calculations, but a robotic agent can make those calculations and then keep a safe distance such that if the car in front applies at maximum 1G force, and I have a certain amount of time before I start reacting, then I'll still not hit the car. So we're making assumptions, and then we take the worst case under those assumptions. And the idea was to say, in all the richness of driving, we can reduce it to 5 principles, state exactly what are those assumptions, what are the parameters of those assumptions, what are the lateral and longitude safe distances that we need to keep, such that we can then guarantee that under this model, the robotic agent will never make a decision that will cause an accident. And in the past 2 years, we're working quite successfully with regulatory bodies all over the world, US, Europe, China, Israel, to standardize these principles. Okay? Now, this is crucial, because if you don't standardize these principles, you cannot be assertive, you cannot take risks. So, if I would say, what is the major challenge in building autonomous car, is this topic. how do you build something that that can satisfy regulation, and regulation is non-existent, so you have to build new regulation. So let's move to the next industry. That's from Orcam, and let's talk about AI for the disabled. And the disabled is rich. It's not just one section of society. So the idea is now, let's look at AI now on me. A small device that I can put either on my eyeglasses or on my shirt, that has a camera and a microphone and has sufficient AI in order to understand the world and provide me value. Right? And then what kind of value and which segment of society can we serve with this value? So when we look at sight, we can read text, recognize people, understand the visual world, react to gesture. With the microphone, we can do transcription, diarization. If there are multiple people talking, we can do voice separation. I'm going to show you examples of all of these. Focus on a speaker, extract emotions, monitor health or mood of people through voice and visual. And then, retrieve information, understand information when I'm looking at text. And now the question is if I can do all of these things on a wearable device, then what can I do? One moment. I just want to say that we do have a wearable device that has sufficient computing power to do AI, and that's the smartphone. The problem with the smartphone is it doesn't see and doesn't hear. It's in our pocket. And if it's not in our pocket, I hold it like this, looking at me because I'm texting. Right? We need, in order to do all those things, we need a device that continuously sees and hears and has computing power. This is why a smartphone, even though it has the computing power to do this and has a microphone and has a camera, it's not being utilized in this way because it's in our pocket. Okay? So we started looking at several sections of society. The first section of society is the blind and visually impaired. And let me show you. We'll start with a clip, and then I'll explain.
Hello, Ben. Can you show us what the device does?
Yeah, sure.
And this is the device. Clicks with magnets.
Oh, it already recognized you.
Okay, I'll just stop here for a moment. So when it sees a familiar face, it will tell the user the name of the person.
Hello, Tim. Can you show us what the device does?
Yeah, sure. Oh, it already recognized you. Let's see who else. Hi, Gil. Hi.
What else can you do?
So the device can read from any printed surface and recognize colors. Let me show you how it works. Take newspaper and read by pointing.
The most coveted free agent slugger on the market has final.
How do you stop it?
So what you've seen here is the following. You've seen face recognition. You have seen gesture recognition, the finger. Also, there's a hand, it will stop. If she raises the hand, it will say the time. Text, layout of text, it will read barcodes. It will recognize products. So this is one section of things. There's about 20,000 units already shipped, 35 languages. But let's see more. Let's see a bit what is going under the hood and additional AI capabilities. So under the hood, the system continuously recognizes and understands the environment and looks for category of objects like doors, furniture, people, screens, stairs, logos. I'll show logos in a moment. Money notes. So I see here people. Oh, this is a business card. It knows it's a business card. See, it knows it's a smartphone. And this is done 10 frames per second. Continuously monitors the world. It looks at the page. It will see the index, so the gesture. Now it does the layout. So it's not only just OCR. It needs to understand layout. Another gesture. Let's have it again. A computer monitor, and so forth. So there is kind of a large vocabulary of things that is important for the device to understand and know, regardless of what the user wanted. Just that the device is now preparing itself. I'm understanding the world. So those are money notes. So let's see a bit more. So now let's take visual understanding and natural language processing and put them together. So let's assume I'm holding a telephone bill and I'm blind or visually impaired. Now I know it's a telephone bill. I want to know whether it's addressed to me. So rather than reading the entire text and waiting until my name appears, I can ask the device, start from Amnon, or is there Amnon? So I can now do information retrieval. Let's assume I'm holding a menu. I know it is a menu. I don't need the system to understand it's a menu. I know it's a menu. And I want to know what's for appetizers. So I can say start from appetizers. So the system will take an image of the entire text, immediately do an OCR, and then do information retrieval. And can start from appetizers. So this is what...
Is there a name?
Mr. Joe Bloggs.
Start from total.
Total due $358.70.
Read me the phone number.
1-800-267-926.
Repeat the last sentence.
1-800-267-926.
So now, so putting together NLP and machine perception can start giving a sense of intelligence to the interaction between the user and the device. But now we can put also NLP and object detection together. Say I see a cup. I don't see, I'm blind. But the system will tell me there's a cup in front of you. So now it can see also my hand, and now we can direct my hand to the cup. So you're going to see something similar, not with the cup, but with...
I see 2 doors on the left. Closed door on the left.
Guide me to the door.
Closed door on the left. Closed door in front of you. Door handle to the right. Got it. 2 people on the right. A table in the center.
Okay, so you see where this is going by, and also the system understand logos. Why it's important to understand logos? Say you are blind and you are your favorite mall. You know the layout of the mall, but now you are disoriented. If now somebody tells you that Starbucks is on the left and McDonald's on the right, you got back your orientation. So this is another tool for gaining orientation. So where is this going? The idea is to emulate a human assistant completely. Right? So it's like somebody intelligent standing beside me, looking at where I'm looking, and having intelligence that I can interact with this assistant, and tells me what I don't see. Whether it's reading to me, whether it's extracting information from text, whether it's recognizing people and objects, and guiding me through mobility. So the idea is that you can see, hear, and understand the environment, and you can interact via gestures and voice. Okay, so here you have a segment of society that, from their point of view, something like this is transformative. Right? Just try to imagine you're blind or visually impaired, and what something like this can do. But now let's go further. What can I further do? So now we can take a device. Now this size, it's kind of a pendant, would be on your shirt. I have it in my bag here, but whenever it's on your shirt. And it has microphone, it has a camera. And now we can solve another major problem that people with hearing disability have. And by the way, all of us at some point will become hearing disabled, right? So it's so one of the issues of hearing disability, since when you're not hearing disabled, you don't know about this issue. But once I'll tell it, it will sound very, very natural. It's called the cocktail party problem. When you are in a restaurant or in a party and many people are talking, and you are having a discussion with someone, we have this miraculous ability to focus only on this person and filter out everything else, even though everything else is not noise. It's other voices. It's the same frequency. It's other voices. So from a scientific point of view, this task is very, very difficult, and has been a subject of scientific research for decades without success. And only in the last 2 years, with the aid of deep technologies, deep networks, some very, very interesting results have emerged. We at Orcam, we took those results and elevated it to be able to handle streaming, so in real time to do this, rather than having the entire voice waveform and then working on the voice waveform, where you see the future and the past, here you see only the past. So it's a much more difficult problem. So if now I have a camera, I can focus on the person in front of me and kind of read the lips of the person. And in that way, filter out. Okay, and it's really, once it works, it's really miraculous. So let me show you. So here's a guest. We gave him a piece of paper, told him read, and his friends were sitting beside him, and we gave them a piece of paper, told them read, and all together, simultaneously.
Any more events involving Israel, the predominantly Muslim country, which is a strong supporter of the Palestinian cause.
The only thing I figured out was Palestinian. Anything else? It's very, very difficult. So now, let's look at the second clip. You see the bounding box on the face, and you see the face on the left-hand side.
And now, involving Israel, the predominantly Muslim country, which is a strong supporter of the Palestinian cause, refuses to budge over a ban on Israeli athletes. In a power swing.
So now we're going to have the ultimate. It's the same person, so now it's artificial. It's the same person, but speaking differences. Let's have a look.
All right, so today I'm going to talk about four things. These are the four critical things to remember. The first relates to how we make numbers.
Okay, impossible. So now let's look at this.
So today I'm going to talk about four things. These are the four critical things to remember. The first is how we make numbers, things like that. For me, it's kind of strange because actually I started guys I was worried. The third thing.
So now think of it at the level of a product, not at the level of an academic paper, right? You are hearing disabled. What happens with hearing disability, that in these kinds of scenarios of the cocktail party problem, people with hearing disability, they have a hearing aid, but that hearing aid cannot cope with this problem. So what the hearing aid does, it amplifies all voices. So they simply take a step back from the discussion. What the environment thinks is that usually hearing disability comes also, it's age related with old age. What the environment thinks is that there's a cognitive deterioration of the person. But in reality, what happens, the cognitive capabilities are intact. It is the hearing disability that is causing the person to take a step back and not engage in the discussion. So now if you have something like this, you have a hearing aid, you have this camera attached here, and whoever you're looking at, you're starting to focus only on this person. And of course you can do more than that. You can also try to do voice separation from a voice signature, not only from the video. So even though at some point I'm turning my head and that person is still talking, I can still filter out that person. Okay, so this is another line of product that is coming out, and where significant AI is taking a part here. Let's look at the last point, and the last point is let's take the same idea of a device that you attach to your clothes, and focus on face recognition and transcription. Okay, now this is a bit spooky when you think about us as a consumer product. So what we did, we didn't put yet the transcription, but we created a device with face recognition and put it on Kickstarter for 1,000 people. That's it. We're not selling it anymore. Just 1,000 people. So it was 900, so that we can start seeing what kind of use cases. Who are the people that use this device, if anyone is using this kind of device? So just to see what it does, the device is standalone, doesn't send anything to the cloud. It has the ability, it wakes up every 3 seconds. If it finds a face, it recognizes it, if that face is in the database of the device. And there are all sorts of ways to onboard new faces onto the device, either through LinkedIn databases, or through simply at the time you are engaging with the person, you can tag the person and enter into the database. So on the left-hand side is a typical day of mine, say September 5, these are all the people that I've seen. Okay, so whenever I see a person in real time, it will send this information to any Bluetooth device. It's my smartphone, smartwatch. This is near, so this is kind of the page of near. He's, by the way, the product manager of this device. And you can see recent meetings, 6 days ago, seen with, so I can get all sorts of statistics about when I met this person. And then on the right-hand side, I can then divide the people that I know into groups. Family, friends, work-related, and so forth. How many groups that I want, and hierarchy of groups, and so forth. So we release this device through... No, I have more friends. No, there's another... there is friends here, and there is another friends below without the diez, and there are more than that. I'm social. Okay, so we released this device to 900 users, and we found out that 10% of them are using this all the time, every day, 8 hours a day. The device works for about 10 hours between charges. And we started then profiling these people. So it turns out that they have kind of light aphasia or light. It's not something clinical, but they claim that they have a difficulty of matching a name to a face, especially when they haven't seen that face for a number of months. And usually it's in a work-related environment. They have many customers, and they meet a customer, and that customer gets offended that they don't know how to match a name to the face. So it's about 10% of this focus group. I'm not saying 10% of society, but if you Google face blindness, you'll see it's about 2.5% of society. So this is interesting. So we'll start now focusing the application around this kind of use case and release this as a consumer product. The second thing is to look at this product in an organizational environment, not in a consumer, because in a consumer environment, the issues of privacy are so severe that there is you can do many things that we cannot do because of privacy. But in an organizational environment, the devices can communicate with each other, can send things to the organizational cloud, and do much more interesting things. So we call this B2B, and one of those areas is hospitals. Now, just to skip the slides, I'll just say it in words. That there are several needs in hospitals. First one is there's kind of patient staff recognition. As part of accreditation of hospitals, a staff member approaching a patient should always ask the name and ID. Next time you're in a hospital, be cognizant about it. Last time I was there a few weeks ago in an ultrasound, 10 times I was asked my name and ID, even though I knew that they knew who I am. Right? It's part of the accreditation that they need to ask name and ID. Second, there are many imposters. I don't know if you know that. There are many people who just wear a robe, put a stethoscope that they buy on eBay, and there are many, many imposters.
Specifically in Shiva.
All over the world. All over the world. There are many, many imposters. Third, and that is the most critical, is 40% of the time of staff members, physicians, nurses, is typing and writing reports and putting codes such that the insurance company gives the maximum benefit to the hospital. And this is really time consuming. Now imagine you had this device, doesn't only see but also hears. You say a code name, and then whatever you say is being transcribed. It knows that this transcription is the context of me looking at David. So it can then create a transcription of my interaction with David or my interaction with Noam, sends it to a folder, in which then I just go and edit it and save a lot of time in writing a report. So this is, for example, Sheba was mentioned here, a pilot that we're now conducting with Sheba. And here we're talking about thousands of devices per hospital. So this could be a very, very big thing. So those are, just to show this transcription, being able to transcribe in noisy environments. We're taking the previous example of being able to deal with the cocktail party problem. Okay, so we can transcribe only the person that I'm looking at.
Show the technology of OrCam
So we need very, very strong transcription abilities. Okay, so now I come to the last one, which is now looking 2-3 years into the future, and let's look at natural language processing. This is another company, AI21, was co-founded with Yoav Shoham from Stanford, a good friend of mine, and his friend Ori Goshen, and looking at natural language understanding, but things that will be in the future, not looking at the current state of the art. So let's see what. So when we look at AI, the success is in very narrow domains. Autonomous driving is a narrow domain. All the examples that I showed you is being able to reach very, very high performance, but on a narrow domain. It's called narrow AI. Okay? And the promise of AI, what we see in science fiction movies and you know what the celebrities are talking about when they talk about AI, is about general AI. Is about AI, is about machines that have more broad intelligence. And this is completely open. There is no such general AI today. When you look at reading comprehension, so let's say I want to read a book and then answer probing questions on that book. Read, the Game of Thrones or War and Peace, and then being drilled and grilled about the plot, about the actors in the plot, about the relationships. We humans can do that. There's no machine that can do that today. So reading comprehension, we can think of it as a microcosmos of the challenges along the journey to general AI. I wouldn't say that this would be now the intelligence that we're looking for, but being able to read and understand what you're reading. I'm not talking about reading a sentence. Reading long passages and understanding, say at human level, is the next frontier, which is not science fiction. All other frontiers we can speculate and so forth, but that will be at the level of science fiction. Here we're talking about something that is within reach, and I'll show you some examples. Okay, and the community in the past 2 years has been working intensively in these areas of reading comprehension, and there are benchmarks, and it's like the benchmarks in machine perception that in 2012 reached kind of a tipping point in which a benchmark which is difficult to succeed, called ImageNet, machine perception have reached human level performance on that particular benchmark. It doesn't mean that machine perception is reaching human level performance on human perception, but on that particular benchmark. Same thing is happening with reading comprehension. For example, a data set called Squads, Stanford question and answering. You have, 5 minutes is all what I need. You have a passage, which is a paragraph. You have a question, and the answer is a subset of the paragraph. Could be a word, it's called a span, or could be a continuous collection of words in the paragraph. And machines today reach human level capabilities on this particular benchmark, and more benchmarks like these are being conquered in terms of reaching a human capability. Okay? So what is required to go beyond simple Q&A tasks? So when we look at those deep learning networks, it's not the expressiveness. They're sufficiently expressive. They can express almost any function from input-output that we think of. This is one of their great strengths. The challenge is about inductive bias, is about focusing the hypothesis space on the areas that matter. It's like tying our hands. Now, with pattern recognition, we were lucky. The connectivity of the deep networks are really tuned to the relevant inductive bias, and that's what makes those deep networks so successful for pattern recognition tasks. But when I'm talking about reading comprehension, you need to think of specialized inductive biases. Just the connectivity of the network is not going to be enough. And here the idea is there a way to combine classical knowledge representations, stuff, research, science that was done in the 80s and 90s, temporal logic, all sorts of knowledge representations that have been developed in the 80s and 90s, and somehow combine them with the new science of deep networks. So here is a network that learns to do the following disambiguation. But when you look at a sentence like Dan cooked a bass on a grill, here bass is a fish. But you look at the sentence below, the bass player was exceptional, here bass is an instrument, right? So this are called synsets. You have the same word in different contexts has a different meaning. And there is a graph called WordNet that people have compiled back in the 80s. The idea is to take this WordNet as a knowledge representation and put it together with a deep network, and being able to understand also the semantics or the synsets of every word. And there is a benchmark called the word in context, where you have two sentences and the word and the same word in both sentences, and the question that the machine needs to be able to answer is, does it have the same meaning or not? And here kick in both sentences has a different meaning, where the state of the art, called BERT, that doesn't really matter what it stands for, it's from Google, says the same. Here plant has the same meaning, but state of the art shows it's different. And when we put our network, see here sense BERT large, it is the leaderboard of this benchmark. So it is the best result. So why I'm showing you this, again, it's not an academic talk. I'm showing you this because it's a preview to the next thing that I want to show, which is cool. That this is interest only academics. But now let me show you something that is cool. And this is text generation. So first, I want to imagine the asymptote of text generation. Why it could be something that's transformative. Let's assume that I can provide you a tool in which you only specify your general ideas, and then the machine will write the entire text. Now, it makes a lot of sense, because if you look how technology has progressed, we use calculators, because I don't know how many of you know how to take a square root of a number, right? We use calculators. I don't know how many of you scientists know how to solve a differential equation or take an integral, because machines do that, right? So our innovation is what equation to solve and not how to solve the equation. Same thing would happen with writing. Why should we now write all the text? Our innovation should be, what are the ideas that we want to express? We write down the ideas and then let the machine do all the rest. Now, my claim is that this is not science fiction. This is something that you'll see in the next 2-3 years. And let me show you something that is quite cool. So what we did here as a surrogate to putting ideas is we wrote a machine which does the following interpolation. You give it the first sentence, the prefix, and you give it the last sentence, and let the machine do all the rest. Now, this kind of interpolation makes all the difference, because all the ones that were before, they started only with the first sentence. You start with the first sentence and then let the machine write text. What the machine does, it writes text that looks natural, but it diverges very, very quickly and becomes nonsense. But once you constrain it with the end sentence, then the text starts looking quite reasonable. So let me show you some fun things. Yeah, here it is. So on the left is the state of the art. State of the art is you give it only the prefix. So the prefix was, let's be honest for a second, women want, women want to have sex, and so forth and so forth. That's okay. But now we give it also the last sentence, right? So let's be honest a second, women want, and then that's why empowering girls is so important. So now when you see the text that is being generated, makes much more sense. So this program was put on the internet for people to start playing around. And you can see here this guy saying, I put the first sentence of my book and the last sentence and filled the middle. I don't think I could have done better myself. Okay? And here we're talking about, really it's a surrogate of the transformative idea that I want to convey. The transformative idea is not, start with the first sentence and last sentence. It's give me in between, give me ideas. And I don't need literally to put that sentence in the middle of the text. Just give me ideas. So you can see the promise of something like this. Only with the first and last sentence, we can do things that are very, very interesting. So we can, and this is the last thing that I'm going to talk about, we could see in a couple of years, 2, 3 years, say 5 years, machines that will be writing for us. So we'll be trained at school to think about the ideas and not just, write them. We don't need to write them. Just like we don't need to do calculations, we don't need to solve equations, we don't need to take integrals, we don't know how to take eigenvalues and eigenvectors. Maybe Noam knows how to do that. I don't know how to take eigenvalues and eigenvectors. You did Python or MATLAB do it for you, right? So same thing with writing. Okay, so these are the takeaways. We have narrow AI. It's progressing very rapidly. State of the art is good enough to transform certain industries, and transportation is one of them. Automotive driving is really the ultimate challenge of narrow AI. It has all the elements, perception and decision making, and very, very difficult because you need to put something at a performance level that is so high that has to reach human level in order to be able to put it on the road. Machine perception can also be transformative to wearable AI, to segments of population like blind, visually impaired, hearing disabilities, face blindness, and so forth. And natural language understanding is a good surrogate to start thinking about general AI. I'm not saying that, we get natural language understanding right, we have now Skynet. I don't know if you like science fiction. Not there yet, but it's a good starting point. Okay, thank you.